Alright, welcome back to our Croof series. So as you might notice, I've made some changes off screen. One of them pretty obvious. I've added a color scheme for our language. And for anyone that's new to this project, what Croof is a really simple programming kind of language. I would call it more of a markup language because I'm not intending it to make, like actual programming in it, but it's a kind of a markup language for defining math formulas and functions, operators, things like that. And then you can actually evaluate certain expressions. And it's not just going to, Python eval this thing. It's actually going to use the operators that you are defining in the language, and then it's going to use built-in or like functions to evaluate the numbers. And it's actually doing things like let's actually see an example of running this script, actually the test.croof file. And what it does is, as I said, it tries to apply like definitions. For instance, here it converts this expression into another expression by using one of these definitions. So it replaces 1 with a successor of 0. Then it uses the shift formula, which is basically, I guess, this one, right? It applies this formula, it gets another expression, then it applies a different formula and it gets a different expression, and so on and so forth until it gets a result. And yeah, I think it's a pretty cool project, honestly. Although it's kind of slow for certain like if you would try to make a really difficult operation, it's gonna be pretty slow. I'm not gonna lie. I guess, it's more of a proof of concept of trying out this idea, but in the end we still need to implement some kind of heuristic or make it smarter somehow. Like right now it tries all the formulas, it sees which one gets to a good result, and then it says, okay, that's the result, but it doesn't have like an idea of how to use the formulas. It's just applying them in a breadth first search style, right? So it tries all of them, like backtracking. So yeah, that's pretty sad. So I guess what was the feature that I was talking about? Well, we should go into the solver to see that, right? And I guess one of the examples might show it better. So I have this stdlib.croof file with a bunch of mathematical definitions and, I don't know, booleans, comparison, and comparison is also going to be an operator, right? So hopefully it's not way too sudden to look into these kind of symbols for someone that's new. Like if you saw the previous parts, then it should be pretty straightforward. So yeah, my idea was that, well, if you have something like a comparison, you might need to define it recursively in terms of other numbers. So if you want to compare, let's say, 1 with 4, for instance, you would have to first compare 1 with 2, 1 with 3, and then 1 with 4, right? So, or something like that. Like you would have to make incremental steps. And my idea was, okay, if you have a number and its successor, then it's pretty straightforward. A number is less, it's like smaller than its successor. Obviously, that's true. But if you have two numbers that are like 1 and 4, which don't have any relationship between them, you might need to define it recursively. So you could say something like okay, let's say we compare 1 and 4, and we convert the 4 into successor of 3. So we can apply basically this formula if 1 is less than 3. So it goes into this recursion until it reaches the base case, which is this one. And this is the feature that I was talking about that I implemented off screen. So I would like to maybe showcase it, and then we can try to implement something cool like Fibonacci numbers or something. So let's go into the solver, or maybe actually let's examples. Let's actually see how it looks like for the proof, right? So it tries to prove that 1 is less than 4. So it applies this formula, which converts it into 1 is less than successor of 3. Then it applies it again for some reason, right? Also applies this one, I guess. 1 is less than successor of 2. Then it finds that 1 is less than successor of 1 because that's one of the base cases, right? And then it shows that 1 is less than successor of 1 because it already proved this thing. So yeah, it like goes into this recursion, right, to prove step by step, and then it goes back to the actual thing that it had to prove, right? So it gets a true. And of course, just so you know, you can see that it actually works. If I use, let's do 2 less than 4, still works. It was a bit slow, but if I do 2 less than 1, it's gonna say that no solution was found. I'm not sure yet how to do the otherwise case to make it false, but yeah, it's just gonna say that it cannot solve it. So that's good enough for me, honestly. So it is what it is. Okay, so how I made this thing work? Well, let's go into the solver. So I added this extra function called proof, and the idea is this one needs to I guess the difference between solve and proof is that proof has two expressions, one on the left hand side and one on the right hand side, and solve just tries to get the expression with the least degree, so like a number, let's say, or a variable. But proof is gonna try to get the expressions matching, so it's gonna change the left hand side expression until it matches the right hand side. So that's what proof is gonna do compared to solve. So then also inside of the proof, again, we just apply the mappings, we just modify the left hand side until it reaches the let's say the right hand side expression. So that's all it does in a sense, right? And how I change the function of substitute was that, so substitute helper, what it does, so before it was creating a mapping and then it was just applying the mapping, but now we have this intermediate step called proof all, which is going to look at all the conditions from an implication, and it's going to try to use that mapping to prove those conditions, right? And if those conditions are met, then it's going to apply the mapping on our expression. So we have this extra step here that just makes sure that the conditions from the implications are correct using our mapping, and that's going to give us a list of steps, and you can see that those steps are like these ones. I'd like to maybe put them in a better order somehow. I'm not sure what order to put them in. I thought that the best order would be from the smallest expressions, so like solving small expressions and then solving the big ones would be the best approach. Maybe using different indentation for them would be another idea. Not sure. But still works. So if you put all of these expressions in a list, still makes sense to use them like that. So I think it's fine, honestly. So let's just leave it like that. So this is the main idea. When we create a mapping, we have to make sure that that mapping works with the conditions, and I did that everywhere, right? I just copy paste it, right? So pretty straightforward, this extra step of proof all. Okay, so I guess now what's left to do would be to try to solve a harder problem like Fibonacci numbers. So let's call fib.croof, and let's try to implement the Fibonacci function. So first thing that we have to do in Croof is to define our function. Like if you want to use a function, you just define it. So it's going to be a function that takes in a single number, so that's the nth Fibonacci number, and it's going to give us another number. Then after we define the function, we can actually use it, create some mappings for it. So for instance, Fibonacci 0 is going to be 1, Fibonacci 1 is going to be a 1, right? And right now obviously we can just try to use it. Fibonacci 0, so let's do 0, 4. So it should just work like, oh, Fibonacci 0 works. That's cool. You can even have Fibonacci 0 plus Fibonacci 1. So what would happen here is, well, that's interesting. It looks like the second Fibonacci number. Maybe, we are onto something. But you can actually use the function. However, if you put a 2 in here, as you would expect, it's not gonna work. We don't have a solution for fib2. That's kind of lame. So let's try to get it to work. So we saw that for 2, what we can do is add these things. So this should work, right? Okay, nice. So it just works. But you would have to write this thing by hand. I'm not even sure. I think fib3 is going to be way too complicated, honestly. So fib1 plus fib2. I think it's going to be, it might take too long to solve that, which is kind of sad. That's why I would like to have some kind of heuristic for the solver, because it's really slow, because it has to try all the formulas. Right, so yeah, that's kind of lame. But you can see that you just have to write all of them by hand. So what if instead we are trying to use some kind of variable? So for that we use the for all to define a variable. So we say for all x in n, and then we can just define the recursive call. So fib. So what can you see here? Like, what's the relationship between these three numbers? Right, we have the number x, right, which is the smallest one. Then we have its successor, and then the successor of the successor. So what we can do is say something like fib of successor of x is equal to fib dot x, I guess fib, and the argument is x, and successor of x, right? So this would be the recursive definition. And if we just call this thing, right, it's gonna give us a 2, and it's still gonna use, I guess, does it use the right formulas? Probably should use them, right? So it converts it into fib1, then it converts it into fib successor 0, then it knows to apply this formula. It gets fib0 plus fib successor 0, 1 plus something, gets this thing, fib1, then 1 plus 1, and then 1 plus 1, it already knows how to solve it. So again, maybe we can have things like caching, because if you solve 1 plus 1, you can do something like, okay, already solved 1 plus 1, so there's no point in solving it again, right? Now, yeah, the problem with, oh, I have to call fib3, it just takes too long, honestly. But you can, like, there's no issue here. Maybe just to see how that would look like, what we can do is come in here, and we can actually just maybe print ln try, I don't know, like just the expression. Maybe we can just print the expression, right? But yeah, it's like gonna try all the possible cases, so this would be the next step of what we can do, like on the list, to try and get this thing to use an heuristic maybe. But the heuristic cannot really be based on the degree of the expression, because sometimes to get to a good solution you have to go on a rough path. You know what I mean? Like the path to solution might look really weird, but I don't know, like some of these expressions are pointless, right? So it's obvious that some of them are repeated somehow, you know what I mean? Like maybe we can have some kind of hashing of an expression, and if two expressions are too similar, then we can just ignore them, but not even sure about that. It's like pretty difficult to say it. I don't know, it feels like a really difficult problem. But yeah, like you can see that at some point it gets to a really simple branch, but like this one, for instance, this one should be the path to the solution, in my opinion. Is like fib0, which is well known. This one is also known, right? But it gets to this annoying yeah, maybe the degree could be a good heuristic, so we could try to do that and see what happens. But that means we have to implement AStar, so who's in for the ride, I guess? Should we try to implement AStar, or should we just, I mean, obviously we are gonna implement AStar. So let's see. I'm curious how it's gonna go, because for AStar Wikipedia, AStar search. So I think that's what we are gonna try to do today. Try and use AStar, which is basically BFS, but instead of trying, I mean, it's still gonna try all the neighbors, but instead of trying them in the order that we give them, it's gonna try them in a certain order, right? So we have the open set, which is the start. I mean, I have to use, I don't know the algorithm by heart, so it is what it is. Came from, we already have it, it's called parent. I guess open set is just visited, or I guess Q probably. Then we have a G-score map for each node, makes sense. G-score is basically the cheapest path from the start to the current node. Then F-score is G-score plus the heuristic. So The heuristic is gonna be a function that we decide on, and is gonna represent the approximation from going from the current node to the end, right? Then open set looks like the queue, honestly. Oh, but it's not gonna be a queue, it's gonna be a priority queue. Priority queue, and it's gonna be sorted by F score. So it's interesting. Let's see Rust. I mean, it should have a min heap. I think it's called binary heap, right? So we have a heap. That's good. Rust priority queue. Do we have a priority queue? Doesn't look like it. We have a crate, but I'm not gonna use it. Okay, I mean, we can use a binary heap. Okay, anyway. So we are gonna use a binary heap for the open set. Then if the current is equal to the goal, we are gonna give it a function like this. I mean, I can rename it is target, because it looks annoying. I mean, it's gonna be called is target. Okay, if it's a target, we are gonna reconstruct, so same thing, right? Then we are gonna remove the fuck. I mean, yeah, I was looking at it, what the fuck? We are removing the node for each neighbor. So here we generate the neighbors with this substitution function, all right? But we are just gonna call it neighbors. We are gonna generate them, and then we have to look at the scores. So this is gonna be the important part that basically sorts the neighbors. So let's try to implement that. So instead of solve helper, let's copy paste it. Let's call it AStar. Solve AStar. Or maybe what I can do even, but I want to compare them. So let's leave it solve AStar. Okay, so it's still gonna have the thing. So visited, I should still keep it. Not sure, honestly. Looks like we don't need a visited, which is kind of weird. So instead of a queue, we are gonna have a min, or I guess a binary heap. It's called binary heap. Okay, it's still gonna be called queue. Is what it is. Okay, but instead of doing a pushback, we have to do something like q.push, and here I guess it's some kind of element. I'm not sure if I can push. Actually, let's have let mutable g score is equal to, so this is going to be a hash map new, and it doesn't really matter. By default, we're going to return infinity. gscore.insert, and we're going to insert the expression and 0. So obviously the score from the beginning to the beginning is 0. Then let's create fscore is a hash map as well. fscore.insert, and here we have the expression, and let's have an heuristic function. Heuristic, and it's going to return I32. heuristic of expression. Right, so we have the two things. Perfect. Came from, we have it, open set. So now inside of the open set we should I'm gonna call it start time, or maybe h, just for the memes. So I think I can do something like expression h, but not completely sure. Ord is not implemented on expression node. Okay, that's cool. So I guess, like, I don't want to do anything if that makes sense. Let's try to implement ord on the expression. It shouldn't do anything. I'm being honest. So ord for expression node. So compare. So it should always be equal. Okay, so it wants partial ord. Sum std cmp equal. What the fuck? Ordering equal. Oops. And then F capital R. Okay, no. And if I want to implement ord for expression, it shouldn't ask for anything. It should work like this, I guess, or it doesn't. And that's weird. I mean, I should be able to just say here ord. Oh no. Okay, whatever. So it's just gonna do that. Hopefully that's fine. Okay. Oh, I called it H. And here it should work to push this thing, right? So it's a binary heap with these two values. So what we are gonna do now is we take the node with the lowest F score. So can I do something like min pop removes the greatest item? Okay, that's weird. Binary heap min heap reverse. It's pretty cool. So if I can wrap it in reverse. What is this shit? Anyway, like we just use reverse apparently, and if I do pop, we should get the lowest item first. Okay, so this is expected. Whoa. Yeah, it's an option. So we are expecting a reverse expression and the score, which is not important, I guess. Wait. Right. I mean, we should use the F score at some point, but I don't think we need it. Anyway, so if it's target of expression, we just trace the steps, that's fine. We already removed it. Then we have to generate the neighbors. So let neighbors is equal to vec. We create a new vec. Right. And here we should insert these things. Yeah. So the neighbors are gonna be basically substitution. I guess I have to do clone, I don't know, implication and vec empty. I think that's what I want to add in the neighbors. And then here I'm gonna do the same thing, but we're gonna use the steps instead. Okay, and here it's vision. What do I want? It needs to be mutable. Okay. So we go through all the built-in substitutions, we add them, we go through all the implication and we generate the substitutions, and we have the neighbors. And basically the neighbors are gonna have the substitution expression, so what we need to test, the implication node which was used, and then the extra steps that were made to, you know, if the implication had any preconditions. Okay, so those are the neighbors. We have to iterate for neighbor in neighbors. I might have to do something like that. So let's do substitution, implication, and steps just to have them already split. Okay, so we need to generate the tentative G-score. Let's take this in. Let's do a let tentative G-score, and this should be the G-score of the current nodes of the expression. G-score get expression. I think so. G-score initially is infinity. So I might want to do or else, or oh, it's unwrap, or I32 infinity. How do I do infinity in std I32 max, I guess. Okay, so we get the G-score. Do I have to do reference to fuck? Okay, so we get the tentative plus the heuristic, obviously, plus heuristic of the No, it's the distance from the current to the neighbor. So we need some kind of distance function. Distance from the expression. Oh, actually it's going to be expression dot distance substitution. And I mean the distance is going to be 1, honestly, but we'll see. We'll see if I need to change it somehow. But for now, let's say that we go here and we say something like pub fm distance self. Other is also going to be the other self, step self, and it's going to return I32, and for now it's going to be 1. Right, so the distance between two expressions, I'm going to say it's 1 for now. We'll see if I need to change that. And then if tentative g-score is less than the g-score of the neighbor, so g-score get substitution, unwrap or std 32 max. I don't know if maybe there is a way to have a hash map with default. Last hash map with default. Probably there is something, but I don't know. Okay, so if the g-score is less, then we have to set the parent. So we have to do the same thing we were doing here. Right, we set the parent, substitution expression, blah blah. Then we set the g-score of the neighbor, so g-score dot insert substitution, tentative g-score, and then we compute the f-score. For the substitution, which should be tentative g-score plus heuristic of substitution. All right, heuristic. And if the neighbor is not in open set, we have to add it. If q dot contains as iter dot contains, shit, how do I check if the item is in the open set? Must check if item is in iter. Is in vec, okay. Is in vec. And contain, I mean contains, so if it doesn't contain it, so let's do let f. I should do something like q dot push substitution and then f. Reverse. Contains. But I can't even do that. I have to do a for blue. can't I do something like, let's say we have, besides the queue, what if we also have like a visited kind of open set bullshit? So the idea is we remove the item from a hash set, it should be faster. So let mute open set is a hash set new, and here when we change the queue we also do open set dot push expression, or I guess it's insert expression, and here after we pop it we can do open set dot remove expression, right? And here to make it easier we are gonna do open set that contains substitution. So we use two variables, but open set dot insert substitution. So basically we have one variable for containing the hash of the expression, and then the queue is the ordering. That's my idea. So what do we want here? So this is I32 and gives me fuck. I get it. So this should be I32, I guess. Do I have to dereference it or something? Oh, Jesus. I guess I need to reference them. Probably I have to clone something at some point, no? Maybe here as well I have to clone it. And here I have to clone it, I guess. The fuck? Okay, let's rename this to open set and do not G score because Rust. What do you want? Oh, that's fine. Well, this is the Rust experience, I guess. Man, this is annoying. So what's the problem here? So here we have I32. What's wrong with this thing? I mean, for me it makes sense to do neighbors like that, like have a reference. I mean, it's kind of hard to base your shit on the LSP. Let's run the compiler. Let's see what it wants actually. So creates a temporary value which is freed while still in use. Well, I mean, well, who gives a fuck? Just copy that shit. So here we create neighbors. Alright, which should be a vec like that. Makes sense. Substitution, whatever, G-score, let D, let's say let distance, just so we have less shit here. What do we want? Borrow later used here. Do I have to? I think I have to do that. So this expression is, I mean, it's already a shit. Oops. But I don't get this thing. G-score insert. Like, why don't you want to clone it? Man, what a trash language. I'm just kidding. Temporary value, what the fuck is this? I mean, if I'm gonna use a let, it's gonna do the same thing. Like, there's not a fix, I think. But why doesn't it just let me do this stuff? It's like so stupid. Is it really? Like, it doesn't make any sense if... Yeah, I don't get it. Let's see, so G-score is... What if we make it a hash map from expression to I32? Right, maybe there's a problem. Because that's something with reference. Alright. Or some stupid stuff like that. Here expression is also... Maybe let's clone it, right? And in open set, let's also clone it. So here it's expression, here it's... Here it wants that. This one needs what? Insert needs a value, so it's fine if it's like that, I guess. Okay. Maybe we can also hash map expression. let's put the types. Maybe actually typing stuff makes things easier. Hash set expression, but it looks like it already knows the type, so that's the annoying part. Okay, so here get works with the reference. Here insert works with the value directly, no reference. Contains works with reference. Push works with the value. And insert also with the value. Yo, what the fuck? Heuristic. And do I have to clone it? I don't mind to clone this stuff. Don't really care. Let's clone. Jesus fucking Christ. Okay. So this should, alright, I guess the moral of the story is try to put the types maybe. Right when you define a variable, I'd say. Okay, anyway, so this should be the AStar. Right. So let's try serve.solve AStar. Let's pass in the expression. Let's pass in the target function, which is this one. And we also need the heuristic function. So the heuristic function is interesting. What if the heuristic is just the degree? Let's start with this for now. Let's start with the degree as I32. Right, and then for the proof function, we might do something similar, but here it's expression is equal to relation dot right. And here it's relation dot left. Let's see what if this one works with addition first. Nothing changed. That's cool. Does it work with the boolean? Oh yeah, also for boolean. That's also fun one. You can see we have boolean as strings, and it can actually do operators on booleans. That's pretty cool. The conditions still work, and fib still slow. Oops, 04. But it's fib4, that's the hard one. Let's do fib2. Fib2 is the easy one, so it should do it instantly. Fib3, it actually was faster, right? We never saw the result of fib3. Holy shit, we are onto something. We are onto something. We are on fentanyl, but that's the other story. Okay, so let's see here, println. Let's look at the expression. Let's see what it does. So that's nice. So it's gonna try to, not sure, I mean, it's, for me it's magic how AStar works. It's yeah, like we have this G score, which is the cost from going to the start of the current node, F score, which is the approximation, kind of, it's like cost from going from start to current node plus the heuristic of going to the end. The cool part is we don't really know what's the target, so yeah, that makes it harder. Anyway, so yeah, and then this part is actually the magic part, because this one is pretty simple. We take the node that we consider to be the best, we generate the neighbors, right? We even have a function for that, I'm pretty sure. Substitutions. Yeah, I've created this function earlier. I was thinking of something, so we can just use substitutions. So actually we can just say let neighbors is equal to self dot substitutions. Oh, and even better, we can just remove all of that. So we just get all the substitutions, right? We compute the distance between the current expression and the next expression, which should be 1. I'm not sure if we want to do something special here. Maybe it can be the difference in degrees. Like if you, but it's like if the difference in degrees is 0, then that's a bad substitution. If the distance can increase, it's like weird, right? That's kind of weird what to do with the distance. But anyway, so then we take, okay, what would be the g-score for wait, what would be the g-score? Tentative g, oh, so this is like what would be the g-score for the neighbor. It would be the g-score until the expression plus the distance. And here I'm thinking like the distance is gonna be 1, but what if we come up with something more interesting, like difference in degrees or something, I don't know. So this would be the g-score for the neighbor. And here we check, is the g-score better? If it is, then we have to try this path again. That's kind of the idea, right? We override the parent. So we say you can get a substitution to this substitution from the current expression using this implication and extra steps if there are any. So that's the idea here. And then we just override the g-score. We compute the new f-score, which is the new g-score plus what we think is gonna take until the end. And then we insert it into f-score. And then this part right here with open set is kind of interesting. I'm not sure about it. If we don't have the neighbor in open set, if we don't have it in open set, we push it. Like this is the part that I'm not sure about. The part that I'm not understanding, honestly. So if we don't have the neighbor in the open set, we add it. But what if we have it in the open set? Like, how can that happen? Is it like going backwards, maybe? I think it's like equivalent to going backwards. So if, let's say we have an expression, we apply a formula on that expression. So I think the best example would be commutativity of addition. Let's say we have 1 plus 2, we apply commutativity, we get 2 plus 1, and if we apply again, you get 1 plus 2 again. So I think it refers to that case. Maybe we already have it in the open set, so we don't add it because it's like going backwards. It's like in my BFS approach, I had I had visited. Here we have open set. Yeah, I mean, I don't know, it's still quite interesting for me how well this algorithm works on any kind of problem that involves some searching. So if you have a function that looks like isTarget, a function that looks like heuristic, and a function that generates some neighbors, then you can bet that you can solve that problem with AStar. I mean, it's still far from being solved. It's like super slow still, but it's better than it was before. We can generate the next Fibonacci number. That's an improvement, I'd say. Like before that, we weren't able to do that. So wait, did I remove the printf? I guess I removed the printf. Println expression. So we just got a better result. So yeah, I mean, it's gonna be interesting to think about a better distance function, a better heuristic function. Those would be some good goals, I guess. Oh shit, it got it. Damn, that's cool. And here we have the step-by-step solution, right? That's the part that I find really cool, that you can actually see step by step like how to solve it with basically sticks and stones. Like it's like, okay bro, just convert everything into zeros and ones and solve the problem. Like it's like solving the problem on your fingers, right? I mean, sure, we could have solved 1 plus 1 using Python eval, like that's true, but I don't know, I wanted to be able to solve these things, like define an operator, you define how it works in like a pattern matching fashion, and then when you apply it, it's not like, oh, we know it's plus and it adds two numbers. We know that it has this property that it converts from this thing to this thing. It's not like we know what plus does. It's just, converting stuff, which is pretty cool. So it got to 1 plus 1 plus 1 plus 1 in the end. And from there, it's pretty straightforward how to use successor and all of that. So yeah, it's really cool that I find it really cool that it gets to this kind of expression. Like it tries to get rid of all the functions, like it got rid of fib, and then it did something with only numbers. I'm curious now that we have Fibonacci working pretty well, which is kind of hard. Will it work with multiplication? 2 times 2. It worked really fast actually. 3 times 3. Let's make a break here. I mean, it's still some multiplications, and oh, it got something, it stopped there. Like the important part is to get rid of all the multiplication symbols and get to addition. That's what I think it should try to do. But that's easier said, because I'm thinking in like, I already know that plus does something, multiplication does something, like star does something, and if I would solve it, I would try to get rid of the star first and then get to something with pluses only. So here you can see it was doing a big break. Anyway, it got to pluses only, so that's good. It should get to the solution pretty soon, I would say. I mean, it's 3's plus 3's, who knows. And I guess oh boy, was there a multiplication? excuse me. But yeah, I don't know if I want to wait for it. Let's just kill it. I mean, it's pretty close, so I would say it takes a couple of minutes maybe, but yeah. So 2 times 2 was pretty fast. How about using 2 to the power of 2? Nice. So yeah, I mean, small numbers, it gets them, right? 3 to the power of 2, that's gonna be important. I mean, it's 3 times 3, so what am I expecting, right? But what about 5 plus 7? 12. Yeah. Interesting. But, you know, I'm happy with 2 plus 2 working. So, yeah, I guess this is pretty cool, not gonna lie. Maybe one last thing that we could try to implement is some kind of interactive CLI where you can see a formula, then you can see a list of substitutions, and you can choose which one to apply. And then you say, okay, I want to apply this one and then this one. And that way you can actually solve your own expression using this tool. So it will be like an assistant. Because you can see that for big expressions it's not capable of solving them automatically, right? But like that would be a fun challenge to try and solve some expressions. So I think that would be maybe something, I don't know, you can let me know in the comments if you want to see something like that, or you know, I'll implement it on my own, maybe show the result. But yeah, I think this is pretty cool though. Like we managed to implement the AStar version quite easily, not gonna lie. It was easier than I expected. So yeah, and we actually have Fibonacci numbers. Obviously, like implementing FizzBuzz or Rule 110, that I don't think it's Turing complete. So I don't think that's possible. I mean, it's not really intended to be a programming language, right? It's more of a tool to do math stuff. So, but really cool, not gonna lie. It's like, yeah, really like the syntax. It's pretty nice. So I guess that's all for today. And as I said, let me know if you would like to see something like trying to implement it as an assistant, so you can input which formula to apply or something like that. We'll see how we can do that, maybe if you have suggestions. But I think that would be a nice feature besides the automatic solving. And yeah, if you have other suggestions what we can improve, like maybe add some caching somewhere, I don't know, something like that. And also, you know, you can check the project, it's always in the description. Most of the most of the things that I'm showcasing are gonna be in the description or on my GitHub, so yeah, you can check that. And yeah, let's see in the next one. So